Still feeling cooked for the AP Chemistry exam on Tuesday? Well, this video is for you. I'm going to cover all of the big overarching concepts and big ideas you need to master the basics for this tricky exam. So let's get started. My name is Corinne and I run Chem with Corinne. You've probably seen me embarrassing myself on social media. I am a master's level chemist who found out while I was a TA at UVA that I loved teaching and coaching high school cross country a whole lot more than working in astrochemistry. So I switched gears and I became a teacher and I've been teaching chemistry ever since. So enough about me, let's dive into all the content. The goal of this review is to focus on the big overarching concepts that you need to know. We will actively engage with some practice problems along the way, both MCQs and FRQs. And then I really just want to boost your confidence in your content knowledge. You have put so much time and work into AP Chem this year, right? You haven't dropped the class at this point. You know chemistry. And the exam's just your day to actually show it. You're not going to know how to answer every single question, but there's a good chance you still know enough to pass. I will be going through a lot of the questions that I received in my DMs. If you check out the live session towards the end of that almost 2-hour live, you will find me just jumping around answering all those questions that came in the chat. Also in this presentation, if you check out the video notes, you will see the link to this presentation. I have linked videos. Every time you see a little laptop icon or a screen capture, like just a screenshot, click on that and it will bring you directly to a quick tutorial or a short video to help you with some of these concepts. All right, let's jump in. So let's talk about the buzz phrases that you need to be really confident with. The first one's going to be effective nuclear charge. What does that describe? Just the magnitude of positive charge in the nucleus. Literally, that's it. So when we think about the atomic radius trend, as I move across a period, I am adding protons to the nucleus. I'm not adding energy levels. We're all in the same energy level, but I'm adding protons and I'm increasing the magnitude of positive charge. We call this the effective nuclear charge. So as the effective nuclear charge increases, the magnitude of positive charge increases and the electrons are more attracted to the nucleus. So this is going to impact our atomic radius trend, shrinking the size of the radius as I move from left to right across a period. But we'll come back to periodic trends, I promise. And that leads into Coulomb's law, which is that the force is proportional to the magnitude of charge and inversely related to the distance between two charges. And when I'm thinking about chargings, I'm thinking about either positively charged protons, negatively charged electrons. That's what we're talking about, right? So the larger the magnitude of charge, so if I have a cation that has a +2 charge over a +1 charge, the +2 charge is going to have a stronger attractive or repulsive force. We're talking about both types of electrostatic forces, which are just those forces of attraction between particles that have opposite charges, or repulsion, right? Things that are pushing away from each other when they have the same charge. And then that's also the shorter the distance between those charges, again, the greater those forces are. All right, so when we put all of that together, as the effective nuclear charge increases in the nucleus, Coulombic attraction is going to increase because there's a greater magnitude of charge. That means the attractive forces between the positively charged nucleus and negatively charged electrons will be stronger. That means the size of the atomic radius is going to shrink. And then when we tie that into any of the other trends, right, as the atomic radius is smaller, that means the electrons are closer to the positively charged nucleus. It's going to require more energy to disrupt that attractive force. So therefore the ionization energy is going to be higher. But again, like I said, we'll talk more about periodic trends in just a second. You really need to know the distinction between Q and K. So let's start with K because that's what you're most familiar with. You have done a lot with equilibrium constants at this point. So that's just going to be equal to the concentration of the products over the concentration of the reactants raised to the power of the coefficients in that balanced reaction. Solids and liquids do not impact equilibrium, so you will not see those in that K expression. Now let's look at the reaction quotient, Q. It looks like it's measured in the same way, and it is. The difference is the reaction quotient is used to describe any point other than equilibrium. So if we are at equilibrium, we're using K. If we are not, we're going to use Q. Why do I care, right? What does Q actually tell me? Q is going to tell us the direction the reaction is going to shift to reach equilibrium. So if Q is greater than K, the reverse reaction is favored and we are forming more reactants. Think about it. So Q is the concentration of products over reactants. If Q is greater than K, that means we have a higher concentration of products. We have a higher concentration of products, the reaction is going to move in the reverse direction to counteract that. If we have Q less than K, the forward reaction is favored. So we are forming more product. If Q is equal to K, then we are at equilibrium. We're thinking about K, the equilibrium constant. The magnitude is going to tell us which direction is favored. What are we forming at equilibrium? So if K is greater than 1, we say that is thermodynamically favorable. That's a product's favored reaction. Q is very small, less than 1, the reactants are favored. And if Q happens to equal 1, well, what is Q equal to? Q is equal to the concentration of products over the reactants. So if Q is equal to 1, that's one of the rare cases where the concentrations of products and reactants are equal at equilibrium. All right, you heard me talk about thermodynamically favorable. You need to know all of the conditions which are thermodynamically favorable. And yes, you can say TDF. When it comes to abbreviations on the exam, it is okay to use abbreviations as long as you define them. Keep in mind, too, that the test is graded on a question-by-question basis. So if you define thermodynamically favorable, parentheses TDF, don't expect your reader to know what that is in question 7. So make sure if you want to use abbreviations, define them with each question. All right, but let's look at these. Hopefully you already know this. So basically you want to focus on what creates a negative Gibbs free energy, or delta G, because that's what's going to be favorable. So for that to be favored, we need a negative or exothermic reaction, so a negative delta H. We need a positive delta S, so an increase in entropy. K greater than 1, so we are favoring the forward reaction. And then if we're looking at cell potential in electrochemistry, the E dot cell, we want that to be positive. So let's look at an example, because I've been talking for a while. So this reaction is not favorable under standard conditions, but as the temperature decreases, that changes. So which of the following is true? So right away, I would look at these 4 answer choices and I would say, okay, I can eliminate C and D. I know this is going to be a hybrid exam, but guess what? You have tools built into the Blue Book to help you do that. Cross things out, flag questions for review, highlight things if you can. Use the tools that you have access to your advantage. So knowing that, I know a thermodynamically favored process has a negative delta H and a positive delta S. So knowing that, I'm going to cross out D, because we know this is not a favorable process until we have low temperature. I also know that if I have the opposite conditions of what is favored, they are never favorable. So right away, I'm going to be limited to just A or B as my correct answers. So now the question is, how do I remember? Is it low T or high T? What do I remember? You're going to think about the Gibbs free energy equation. Delta G equals delta H minus T delta S. So if I have to have a negative delta G, and I initially had a positive delta G, I'm going to be looking at low temperatures, right? So when T is low, and I'm subtracting T times delta S from delta H, it still has to be negative overall. So I'm going to be looking at situations where both delta S and delta H are negative. If you want, you can also just memorize this. So negative delta H, positive delta S, always thermodynamically favored. The opposite conditions, never favored. High T, so at high temperatures, you're looking at both positive, low temperatures, both negative. All right, just a little bit about thermodynamic favorability. Again, memorize what is always favorable, or alternatively, just think, I need a negative Gibbs free energy. All right, next big concept that you will see just about everywhere, IMF. So let's talk about the distinction between intramolecular and intermolecular forces first. So intra, that prefix means within, right? That those are the bonds inside the substance. So we're looking at covalent, ionic, metallic bonds. All of those are intramolecular forces. Intermolecular forces are what we typically call IMF. Those are going to be the interactions between particles. So definitely take some time to review the definitions of each of these, so it's really easy for you to be able to pick out and predict what types of intermolecular forces a molecule will experience. All right, so here are the 4 that you need to know. The first one is ion dipole, and I'd say this is probably the one you probably spent the least amount of time on, but it's really easy to figure out. So think about the word ion dipole. We have ions in solution in a polar solvent. So in this case, we have sodium chloride being dissolved in water. Maybe you're going to be asked to draw a particle diagram, making sure that you're showing the positively charged sodium ion interacting with the partial negative on the oxygen atom, and the chloride ion interacting with the partial positive on the hydrogen ion. So just be careful with that. That is actually our strongest intermolecular force, but typically we're going to be focusing on the next three. So a dipole-dipole interaction, you're looking at the interaction between polar molecules. The strength of this is going to increase with increasing polarity of that compound. So the greater the difference in electronegativity in that polar bond, the stronger the dipole-dipole interaction. There is also a specific type of dipole-dipole interaction that you might need to identify, which is hydrogen bonding. Be careful with hydrogen bonding. It's between hydrogen atoms and oxygen, nitrogen, or fluorine. Those are very electronegative atoms, but the kicker is hydrogen has to be in a polar bond. If you only have hydrogen bonded to carbon, it will not experience hydrogen bonding. So be very careful, because hydrogen has to have that partial positive in order for hydrogen bonding to occur. The last one is London dispersion forces, or LDF. Everything experiences LDF. The strength of the LDF is going to be based on the polarizability of that electron cloud, which is going to be based on the size of the molecule and the electron density. How many electrons does it have? London dispersion forces is based on the random movement of electrons, so they randomly end up here, leaving a partial positive wherever they are not. The more electrons you have and the larger the atomic radius, the stronger that intermolecular force. All right, so here's just a review of that. Again, every time you see a little screenshot like that, click the link if you need extra practice with that. So when it comes to polarizability, it's just a tendency of the electron cloud to become spread out. So when that happens, there are going to be dipoles wherever the electrons are not. That's where you're going to have the partial positive. So it leads to all kinds of different things like stronger London dispersion forces. London dispersion forces, yes, they are the weakest of the ones that we just talked about, but they're strong enough for geckos to scale walls. Like, there's still significant interactions in between molecules. All right, so why does this matter? When you're looking at the sizes, the strengths of intermolecular forces, you might have to predict which one has the more polarizable electron cloud, or explain why one is more polarizable and therefore has stronger London dispersion forces. So again, you're looking at the size of that molecule and the number of electrons, or its electron density. All right, another big thing before we go into Tuesday's exam, everyone always wants to know what is not on the test. These are the equations that are not on the built-in equation sheet. With this year's hybrid exam, you are actually going to have a paper copy of the periodic table. You can also bring in your calculator. No, you do not have to erase the memory of your calculator, but your formula sheet is going to be electronic. So that's the one you've hopefully been using all year long, but these are the big equations that are not on there. I'd say the cell potential is a big one, and then just knowing some of the rearrangements so you aren't busy doing, moving the log around with pH equations. It just is helpful to remember these little things. All right, other things to know. You're going to assume the 5% approximation always applies when it comes to equilibrium. So you're always going to assume that X is going to be less than 5% of your initial concentration. You don't even have to say the 5% rule applies. You just assume it and you just go with it and you don't think it twice. You're also going to use 3 sig figs throughout the entire exam. There's a tolerance of plus or minus 1. Most things will have anywhere between 2 and 4 sig figs, so 3 is a safe bet. You always want to check out the given units in the problem. Let's say you have no idea how to solve for the HVAP, but you see that the units have to be kilojoules per moles. You have mass, you convert that to moles, you then use the energy you found earlier, and you got it, right? So even if you don't know necessarily what the question is using, use the units to help you figure your way through that. It's also really helpful to look at the constants and any units given with that, and then make sure that you're not making a silly mistake and forgetting to convert Celsius to Kelvin. Make sure everything matches the units in your given constant. When you sit down to take the test on Tuesday, you are going to sit down, you're going to see figures that you don't recognize, you're going to see terminology that you have never seen before. They do that on purpose. That is not going to slow you down, though. You're going to look at that and you're going to say, oh, I'm going to skip that right now. I'm not going to worry about that. And you're going to come back to it later. You're going to read the actual problem, find out what the problem is asking, and then you're going to rock it, okay? There is no penalty for guessing. The readers also use this idea of error carries forward. If you have a long FRQ with parts A through F, and you have no idea how to do parts A and B, but you know you can rock C through F, you're going to write assuming a molarity of 5.20 molar, blah, blah, blah. You can still get full credit if you show that you knew how to do all of those calculations. All right, what not to say is also important as knowing the buzz phrases sometimes. And when it comes to knowing what not to say, you just need to be very descriptive with your FRQs. I'm not saying I want you writing novels, not at all. But I don't want to hear things like dissolves like, opposites attract, based on the arrows of this trend. That's not actually describing anything. If you want a full video of what not to say, click that little laptop and you'll have access to that. When it comes to periodic trends, though, let's spend just a few more minutes on what not to say here. I don't want to hear anything about the location of the elements on the periodic table. That does not work either. Instead, describe what is actually happening to cause that change, right? So sulfur has a greater nuclear effective charge as it has more protons in its nucleus compared to phosphorus. Therefore, sulfur's valence electrons will experience stronger Coulombic attraction and will require more energy to remove them. Therefore, its ionization energy is going to be higher. All right, just be descriptive. Use all of those words that you have learned this year and show off. Why not, right? Please keep sharing your questions in the chat. I'll be hopping in all day tomorrow just trying to answer those. All right, when it comes to the rest of this presentation, my goal is just to hit on all of the topics that have been coming into my DMs this week. If you have downloaded this slide deck, you can click on any of these and jump directly to those slides in the slide deck. It is a long slide deck, so it's easy to get overwhelmed. Unit 1 should be something that you feel really good about. I would argue these are the topics that students feel most concerned about leading up to exam day, just because they're new. But just because they're new does not mean they are difficult. And yes, you will see mole conversions and stoichiometry on the test. So I know you've got that down, so easy points, right? Let's look at a mass spectrum, though, so we can just talk about mass spectroscopy really quickly. So a lot of students will look at this. You look at these two isotopes, and you're like, wait, the relative abundance, the percent abundance is above 100? How am I going to do this? You're going to breathe, and you're going to count up. You're going to add up the total relative abundance, and then take the relative abundance of each isotope, divide by the total, and still continue on to calculate that average atomic mass. So instead, this becomes the mass of 10 times that percent abundance now of 25 out of 125 total, or 20%, versus isotope 2 has a mass of 11, and that's 80%. The total should equal 100, right, even when you've done this. And then we can estimate with this one right away. I know that 80% is a mass of 11. The mass is going to be closer to 11. 10.8, right, is going to be something. But you can do the math. It's just mass times the percent abundance. Add that up for all isotopes, and you'll have your average atomic mass. So in this case, it is going to be 10.8 AMU. You want to include units wherever you can. It is helpful. You want to keep track of units, because it's just going to keep you from making silly mistakes. So then I go to my periodic table, I find the average atomic mass of 10.8, and I'm going to say, oh, that's boron. Not too bad, right? So some of the other things in Unit 3, sorry, this is just extra practice if you need it. I don't know why I said Unit 3. So another thing that's a big deal in Unit 1 is just Coulomb's law. So we talked about this already. It's just that the force of attraction or repulsion, the electrostatic force is what we call it, is impacted by the magnitude of charge, and it's inversely related to the distance between charges, which actually makes sense, right? The further, if you think about two magnets, the further the two poles of those magnets are from each other, the less they're going to be pulled towards each other. Same thing with these charged particles, right? So the closer they are, the stronger those forces are going to be, and the harder it's going to be to disrupt those. So let's think about ionization energy and electrons in relation to Coulomb's law. So we think about ionization energy. It's the energy required to remove an electron from an atom or an ion. So the first ionization energy, that's the one we typically see. That's just to remove the first valence electron. As we move towards the nucleus, right, we're going to have successive ionization energies. So in this case, we have 3 valence electrons. We would see 3 ionization energies that would have similar numbers. They'd be increasing in energy, because as we get closer to the nucleus, Coulombic attraction increases, right? So it's going to take more energy to remove those. But when we shift from that outer shell to the next inner shell, we're going to see a significant jump in ionization energy. And this is a really really common, like multiple choice question. The ionization energies of period 3 elements are shown above. Predict the identity of that third element. So we have sodium. If we look, sodium has one valence electron. You'll see a huge spike between the first and the second ionization energy versus this next one. Yeah, this doubles here. We're looking at period 3, so we're looking at row 3. So now we're going from sodium to magnesium to possibly aluminum. Let's see. So if we look at this, we have 580 to 18. There's not a huge jump until we get to ionization energy 4. So what that means is it looks like this has 3 valence electrons, which matches up with the answer, right? So with this would be aluminum, as indicated by this massive jump between ionization energy 3 and 4. So if you have a question like this, you're going to be looking for that huge jump, and that's going to help you decide how many valence electrons that atom has. All right, electron configuration. Again, really simple concept, but you will see it tomorrow. So take some time just to review that. The exceptions are here. Remember, when we have the d orbitals do not want to be one less than half full or one less than completely full. So instead, that 4s electron gets excited into the d level with, for example, chromium and copper. So those are the exceptions. The other big thing from Unit 1 is Photoelectron Spectroscopy, or PES. So when you're looking at these graphs, you want to remember that the nucleus is at the origin. As we move from left to right, we are moving out away from the origin or the nucleus. So when you're labeling those, you'll be putting in your 1s2, 2s2, 2p6, counting the size of the peak to determine the electrons. So it's actually a really easy question, just with some practice. Just practice identifying what that graph is actually showing you. And then when it comes to periodic trends, know the definition of each trend. What is the atomic radius actually measuring? What is the ionization energy, electronegativity, electron affinity? Electron negativity is like the hardest one to define, but it's so important, right? Because you're going to be determining whether or not a molecule has polar bonds. And what's that based on? Differences in electronegativity. And remember, with those trends, when it comes back to those trends, everything comes back to the atomic radius. Everything is related to that. Start there, then compare that to figure out what's going on. All right, moving on to Unit 2. I would argue this might be an even easier unit. There's a lot of vocab with this, so if you are stressed about that, definitely check out. I have free Quizlets and quizzes all linked for you to try out. All right, so the biggest thing from this unit is, how do I determine whether a bond in a molecule is polar? So what do we look for? We're looking for differences in electronegativity. If it has a difference that is greater than 0.4, then we will have a polar bond where there's an unequal sharing or an unequal distribution of those electrons. So what you want to do is you want to calculate the difference in electronegativity. You can also look at the location of the elements. Fluorine is most electronegative, so the distance from there will kind of tell us the difference there. Know that the carbon to hydrogen bond is non-polar, though. Just like, remember that. Promise you, carbon to hydrogen bonds are always non-polar, so be careful with that. So looking at this molecule that we have here, we have a tetrahedral molecule with 1 carbon to chlorine bond and then 3 carbon to hydrogen bonds. So I just told you the carbon to hydrogen bond is non-polar, but the carbon to chlorine bond is polar. So now looking at the overall molecule, this is a tetrahedral molecule, but it is not symmetrical, right? Because we have chlorine on top. This means that this will be a polar molecule overall. So we have that very electronegative atom of chlorine on top. I should have actually put a chlorine on this. Sorry, I just grabbed this. And that will make the overall molecule polar. So when it comes to determining whether a molecule is polar, you're going to look at the symmetry of the molecule. Do we have all 4 of the same atoms on there? Even if all 4 of these were polar bonds, it would not matter because all of those dipoles would cancel out. So you're looking at polarity. And as soon as I have a lone pair, the molecule is no longer polar. So if you have polar bonds and it is trigonal pyramidal, if it is bent with polar bonds, it is going to be a polar molecule. All right, when it comes to lattice energy, it's all based on Coulomb's law. So let's go ahead and do just an example problem with this. Which would have a higher melting point, sodium chloride or sodium fluoride? So think about that for a second. All right, so both sodium and chlorine and fluorine, they all have a charge of either +1 or -1, right? So it's not going to be based on magnitude of charge. It's going to be based on the size of those ions. So when we think about this, right, sodium fluoride is actually going to have the higher melting point. Why? Because the fluoride ion is smaller. It has a smaller ionic radius. So that means that the lattice is going to be more tightly packed. Therefore, it's going to take more energy to disrupt that, to switch it from the solid state to the liquid state. All right, so that's how we approach like a lattice energy problem. Again, all comes back to Coulomb's law. That's why the joke is that Coulombic attraction is the answer you need for a 5. All right, when it comes to alloys, these are some of the vocab terms that College Board loves to throw at you and just confuse you. We have 2 types of alloys that you need to know, substitutional and interstitial. When it comes to substitutional, what does the word substitution mean? It means you're switching out with something, right? And that's exactly what happens with a substitutional alloy versus an interstitial. Those are in between all of the atoms. You're just kind of squeezing in there, even though you shouldn't be there. Other thing that you need to know is just a metallic bond where you have electrons that are moving freely throughout that. That's why you can get such a good electric shock when you go to touch something metal off the carpet. All right, Lewis diagrams. Feel really confident about drawing those because you are going to be asked to predict like which structure is going to be the best using formal charge. So when it comes to formal charge, you want to remember it's the valence electrons minus the dots minus the sticks. So the valence electrons, based on the location on the periodic table, minus the lone pairs on that atom. So when you're calculating formal charge, you're only looking at a single atom at a time, minus the sticks, which just represent the bonds. So looking at that first structure that we have here, if we look at all of these formal charges, again, it's just valence minus the dots. So if we're looking at carbon, carbon doesn't have any lone pairs, but it has this triple bond and a single bond, so it has 4 bonds here. So it would have a formal charge of 0. You do want to go ahead and calculate each atom in that molecule to figure out its formal charge. The goal with formal charge is to determine which of these resonance structures are most favorable or most likely. And there are a couple ways to actually determine that. So you want the magnitude of those charges to be as small as possible. I don't want to see +4 here and -4 there for a total charge of 0. It doesn't work. So you want to have a low magnitude if possible, and then you want to make sure the overall charge matches the charge. In this case, we have this polyatomic ion with a charge of -1. We want the overall formal charges to add to -1. You also want the most electronegative atom to carry the negative charge. So in this case, we're looking at between structures A and B. We're looking at sulfur having the negative charge versus nitrogen. Nitrogen is a more electronegative atom. It makes sense for it to carry the negative charge. Therefore, the structure B would be the favorable structure. All right. When it comes to molecular geometry, I hate to say it, but you just got to memorize these. You don't need bond angles or anything like that, but you need to be able to translate a Lewis structure into a molecular geometry. Just make some flashcards, practice with these. It doesn't take too long to remember them. There are some mnemonics out there too. Just Google Vesper shapes. All right, when it comes to hybridization, it's like mixing paint. Hybridization, we're just mixing orbitals. So even though we are mixing pink and blue in this case, you can still see parts of each. It's the same thing. It's the same thing. So if we're mixing S and P orbitals, that hybridized orbital is going to have a mixture of the two of them. How do you predict bond hybridization? It's really easy. Thankfully, you're counting the lone pairs and atoms bonded to that central atom. So if I have beryllium chloride here, we have beryllium in the center with 2 chlorine atoms on either side of it. It doesn't have any lone pairs. It just has those 2 bonds. So that's going to be sp hybridization. And like with many things in chemistry, if there is 1, we don't indicate it. So in this case, we have S1, P1, the 2 together add up to 2. Versus looking at methane, CH4. sorry, it's so blurry. So we have carbon in the middle bonded to 4 atoms of hydrogen. Guess what? 4 bonds. That is going to be sp3 hybridization. So not too tricky. So let's practice with this with just some practice related to my friend AP Bio Penguins. So if we want to find the hybridization of the labeled carbon atoms in penguinome, we're just going to look again at the bonded atoms to that. So carbon 1 has 3 bonds to it, so that's going to be sp2. Guess what? Carbon 2 also has 3 bonds, also sp2. Versus carbon 3, it's kind of hard to tell. It looks like we have 1 carbon-to-carbon bond and then 3 carbon-to-hydrogen bonds. That's going to be sp3 hybridization. So we have a total of 4 bonds represented. The other thing you need to know is how to identify sigma versus pi bonds. So sigma versus pi orbitals, these are just talking about the overlapping orbitals again. Sigma bonds, everything contains a sigma bond. When you have double bonds and triple bonds, that's when we add in the pi orbitals. So if we have a double bond, that's going to be 1 sigma plus 1 pi. If we have a triple bond, that's going to be 1 sigma plus 2 pi bonds. And looking at this structure right now, I'm not going to make you count the sigma bonds, but you could easily say, you could look at the 3 double bonds and say, oh, there are 3 pi bonds in addition to all of the sigma bonds here. So again, remember, double and triple bonds do contain sigma bonds as well. All right. Moving on to the big one, Unit 3. So this unit is worth up to 22% of the entire exam. So a lot of people will say, IMF is like the whole exam. No, look at how much is covered in Unit 3. There's a lot that goes into this. So big things are going to be gas laws, ideal gas law, intermolecular forces, as I said, separation techniques, solubility, photoelectric effect, and the Beer's law. For some reason, we see Beer's law pretty much every year. All right. So we already talked a little bit about each of these IMF, but here are just some more images to show you the differences between them. So dipole-dipole, I think I mentioned earlier the strength of this interaction increases with increasing polarity. And then hydrogen bonding, it's just a specific type of dipole-dipole interaction. It is stronger than dipole-dipole interactions, but it only happens when you have hydrogen in a polar bond interacting with a very electronegative atom. And then London dispersion forces, remembering that everything experiences LDF. So when you are asked to identify intermolecular forces, here are the questions you need to ask yourself. First, are ions present? If ions are present and they are interacting with a polar molecule such as water, then you will experience ion dipole. If you just have ionic compounds, you just are looking at an ionic bond, which is an intramolecular force within that compound. And next up, are the molecules polar? If they are polar, then they're going to experience dipole-dipole interactions. In addition to being polar, do they have hydrogen atoms in a polar bond? And then do they have oxygen, nitrogen, or fluorine? If yes, we will expect hydrogen bonding. If no, we're just looking at London dispersion forces. So everything is going to experience LDF, and again, LDF increase with increasing polarizability of the electron cloud. So let's just practice. So this is dopamine. Which IMF will dopamine experience? I want you to take a second, try to figure that out. All right, and hopefully you've looked at this and you're like, it's not an ion, so it's not going to experience ion dipole. And you're correct, but it is a polar molecule. So looking at the 2 oxygen to hydrogen bonds that I've highlighted, we know that it is going to be polar. In addition to that, we have hydrogen in a polar bond, we have oxygen. This is also going to experience hydrogen bonding at those 2 sites. Additionally, everything experiences LDF, so you know that that's also going to experience LDF. So let's translate that to an FRQ. So in this FRQ, you are given 2 pretty similar structures, and you're given a lot of information. So right away, look at the problem and think, okay, what is this question asking? What is already given in this problem? So we know that both of these substances experience LDF, dipole-dipole interactions, and hydrogen bonding. Yet, salicylic acid or aspirin has a higher melting point, a significantly higher melting point. Why? How do you justify that? You look at this, you're like, how are those structures different? Again, let's look for what we call the acidic protons. Those, so if we look, we have oxygen to hydrogen in the first one, but we have 2 sites where we could experience hydrogen bonding. with salicylic acid. That is a difference. That is enough of a difference to have such a significant jump in the melting point. Why? The stronger the intermolecular forces, the more energy that's required to melt that substance, to disrupt the interactions between those molecules, to switch from the solid to the liquid phase. So the addition of, having 2 hydrogen bonding sites compared to the 1 is the reason for that higher melting point. All right, when it comes to properties of solids, you gotta know the vocab. Again, check out those flashcards linked there. Just practice with those so the vocab doesn't scare you. All right, these are all just pretty simple. Know the ideal gas law. You will absolutely see that. Again, use the units in your constant to make sure that everything matches up and that you're doing that correctly. KMT. So there are a couple assumptions that we make about ideal gases. This might be something you want to memorize too. So an ideal gas is one that has no IMF, so no attractive or repulsive forces between those molecules. We're going to say it has no volume, it moves completely randomly, and the collisions are elastic, so they might bump into each other, but they're just going to bounce off happily. No arguments, no transfer of energy. That's what we say an ideal gas does. When are things going to be most ideal? When the pressure is low and the temperature is high. So you can remember PLIGHT, pressure low, ideal gas, high temperature. Least ideal conditions, the opposite of that. So I'd recommend just memorizing that so you have that in your head on exam day. All right, another thing you're going to see is the Maxwell-Boltzmann Distribution. Be careful. The biggest misconception with this is that this high peak represents higher energy. It does not. Read your axes. Always, when you are looking at graphs, read the axes. Figure out what it's measuring. In this case, the y-axis is measuring the number of particles. So actually, the temperature is the lowest. So technically, the energy of these particles is pretty low, right? So if you look, the Maxwell-Boltzmann distribution just shows that an increase of temperature leads into an increase in the variety of particle speeds. So as the temperature increases, you see the curve kind of widening out as the particles just have a better distribution of different possible speeds. Molarity. Again, we see molarity every year. It is simple. You've been doing this for a long time, but why not get those easy points? I like to also talk about just switching the equation around. So we know molarity is the moles of solute per liters of solution. Molarity times volume gives you the moles. So MV equals moles is a great thing to have in your head, especially as you're doing solution stoichiometry and making predictions about those. The dilution equation is also not on the formula sheet. Just this idea that the initial concentration times the initial volume is going to be equal to the final concentration times the final volume. Because when we dilute something, we're not changing the moles of solute, so therefore we can set those two equations equal to each other. If you also have a one-to-one acid-base titration, you can also use this as the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. Again, doesn't work if it's not a one-to-one ratio, but it is convenient when it is. You want to make sure you're comfortable with all those separation techniques. And when it comes to solubility, you want to remember what's always soluble. So nitrates, acetates, ammonium, and group 1 ions are always soluble. And you also want to know that similar intermolecular forces will be miscible. But like I said earlier, don't say like dissolves like. Explain what's actually happening in solution. Spectroscopy, you will have these equations. Again, like I said, Beer's law tends to show up, so don't be intimidated by it. Just remember this is the equation. It's given on the formula sheet. Use your units to find the missing variable. And then I guess I put solubility in the wrong spot. Again, just focus on what's always soluble and you don't even have to know the exceptions. All right, Unit 4. Again, this is one of the easier ones. You do have stoichiometry in there. And I know stoichiometry at this point is really easy for you, hopefully. But there's still going to be some stoichiometry on the exam tomorrow. So be confident walking in to know that you can at least answer that, no matter how cooked you are telling me you are. Big things from Unit 4, net ionic versus precipitation reactions. When you're looking at a net ionic reaction, you're looking at the formation of the solid precipitate or the formation of water in an acid-base reaction. With stoichiometry, make sure you are keeping track of what the problem is asking for. You are changing whatever you're starting with into moles first before you use those coefficients to switch between moles of one substance in the reaction to any other moles of any other substance. And then you're going to convert back into whatever units the problem is asking for. When it comes to other types of reactions, you also looked at redox reactions in Unit 4, but hopefully you spent a lot of time with those in Unit 9 as well. So when it comes to redox, you do want to have all of these mnemonics down because redox tends to feel counterintuitive. When you are losing electrons in oxidation, what does that mean? You're actually becoming more positive, right? The ions become more positive as electrons are removed. So it is counterintuitive, so just keep track of these mnemonics so you don't make a silly mistake. All right, when you are balancing redox reactions, you want to identify the charges of each species. It's really easy. In this example, we have solid aluminum, solid copper. Those are each going to have charges of 0, and then we're given the charges of each of these ions. Now you're going to want to identify the half reactions. What is happening for aluminum to go from a charge of 0 to a charge of 3+? It went from 0 to 3+. It has lost electrons, so it's going to give off 3 electrons as the product. Aluminum is oxidized. Versus CO2 plus goes from 2+ down to 0. It has gained 2 electrons, so it is reduced. So if we have these two reactions, now what we have to do is we have to balance the electrons. Redox is the transfer of electrons, but right now I have 3 electrons released in my oxidation reaction and 2 gained in my reduction. That doesn't work. So what we're going to do is we're going to multiply each side by the opposite number to get to 6 total electrons so they cancel out, leaving us with the balanced equation. So when you're doing this, just keep track of all those oxidation numbers so you don't make a silly mistake. Include the charges, include the states, make sure everything is balanced, and then you should be good. And if you have done some balancing in acidic or basic solutions, good for you. It's really helpful because you will be doing that in Gen Chem in the future, but it's not on the AP exam, so kind of nice, right? All right, when it comes to Unit 5, kinetics, there's a lot of vocab in kinetics, but I think the concepts are not as tricky. So looking at the basics, the rate is going to be equal to the rate constant times the concentration of the reactants raised to the power of the coefficients. The overall rate is just all of those exponents added up. So maybe you're given some lab data and you have to analyze that to find the order with respect to each reactant. Maybe you're looking at the overall order, or maybe you're going to use that lab data to calculate K. So as K as a rate constant does have units, so be really careful with that. K as an equilibrium constant does not. But with rate laws, it matters. Sorry. I recommend just memorizing this. You probably are going to have a multiple choice question where you're given graphs of the data and asked to determine the order of the reaction with respect to that. You're looking for the linear graph, and that's going to tell you whether it's 0th order, 1st order, or 2nd order. When it comes to the rate determining step, the slow step is going to determine everything. If you're given a reaction profile, you are looking for the activation energy, right? So the slow step, if you have a multi-step profile, probably should have included this in the slides. You're going to be looking for the step that has the highest activation energy. That's going to be the slow step. All right, you also want to just memorize this. Again, with K, you got to know the units, so it might be easier just to have this memorized. All right, it's getting hot in here. We are talking about thermochemistry next in Unit 6. Again, a lot of terminology in this, but a lot of it is not new, and then you see some more of it in Unit 9. So looking at the basics, endo versus exo, heat is gained by the system. You get a positive delta H, not thermodynamically favored, endothermic reactions. Versus exo, heat is lost or released by the system. You have a negative delta H. Also, keep in mind, it takes to break, freeze to form. So it requires energy to break bonds. Then when you form those new bonds, the energy is released. Know how to interpret these diagrams. You always start with reactants, you end with products. In this case, energy of the products is lower than that of the reactants. Energy has been released. This is an exothermic process. If you have a multi-step reaction, which you can, you are just, again, activation energy is going to be distance from the reactants to that highest peak. The highest activation energy is going to be the rate determining step or the slow step. Here are some other definitions to know. Just know the distinctions between this. And then when it comes to heat capacity and calorimetry, you're going to be using Q equals MC delta T. Again, make sure all of your units match up. Whatever the specific heat values are given as, make sure your temperature matches that. And temperature is always the final minus the initial. When it comes to calorimetry, hopefully you got in the lab and you got to do some coffee cup calorimetry. Not the best system. It's not quite a closed system. We'll do a practice problem with this in just a second. But when it comes to this, it's just this idea that the heat lost by something is equal to the heat gained by the other system. So if we're looking at this, let's say we have a hot piece of metal, we drop that into the water, the heat lost by the metal is equal to the heat gained by the water. When you're thinking about the signs associated with this, a lot of students will get really stuck on that. Keep in mind your temperature change is going to determine the sign for you right away. So we're just really looking at the quantity of heat. It's not like we can have negative or positive heat. The sign just represents whether that heat was gained or lost. So let's look at an example problem. So let's say we were doing coffee cup calorimetry. You forgot to put the top on top of your styrofoam cup. How would this affect your calculated value for the metal's specific heat? All right, what is this asking? We just want to focus on the metal's specific heat, or C value. So if I didn't put the lid on, some of that heat's going to escape. How is that going to impact my temperature? If some of the heat escapes, my change in temperature is not going to be as large. So how is that going to impact my overall calculation? Well, the specific heat is going to be too small because of that heat lost to the surroundings. So you got to think through the situation, take it step by step. If it helps you, put some values in, put some arbitrary values, numbers in, just to get an idea. But you want to take it step by step. Okay, how is this going to impact the heat lost? Okay, so I'm losing heat. That's going to lower or reduce my delta T. The equation is Q equals MC delta T. If delta T is lower, how is that going to impact everything else? So just take it step by step to figure out those answers. All right, other things you need to know: heat of fusion versus heat of vaporization. There tends to be an FRQ covering this. Just be careful with it. A lot of students will get thrown by this. Again, if you are looking at the heat of fusion in terms of kilojoules per mole, you have your mass of substance, change it into moles, and then multiply by that to get your energy in kilojoules per moles, because moles will cancel out. Always use your units to your advantage. If you'd like to see how to calculate the heat of fusion or the heat associated with it phase change, click on that laptop to watch a quick video. All right, moving on to enthalpy. All kinds of different enthalpies. I like to start with the one that's different from everything else so you don't forget. So when we are looking at bond enthalpies, or the energy related to the formation of breaking of bonds and formation of new bonds in a reaction, it's always the bonds broken minus the bonds formed. Why is that different? That's the reactants minus the products. If you think about any other thermodynamic process or thermodynamic equation, we're looking at products minus reactants, not with bond enthalpy. So be careful with that. When it comes to bonds, also know that triple bonds are going to be the strongest bonds and the shortest. So as we move from single to double to triple, we are increasing in strength and shortening the length of those bonds. The enthalpy of formation, this is the energy required to form a compound. Again, that's going to be the sum of the products minus the reactants. You'd be given all these values, or you'd be given the delta H of the reaction and asked to find one of the missing quantities. So this is all of those thermo calculations just kind of in one image. Again, if you look at the first three, it's always products minus reactants other than bond enthalpies. So don't forget bond enthalpies. Other thing you need to know from Unit 6 is Hess's law. Hess's law is like just solving a puzzle. You're putting those pieces together. As you put those elementary steps together and you figure out those reactions, anytime you flip a reaction or you multiply it, make sure you're doing the same thing to your delta H. All right, let's do a sample FRQ. So in this one, we have the delta H vaporization for NCl3, or nitrogen trichloride, is 32.9 kilojoules per mole. Calculate the energy required to vaporize a 15-gram sample. All right, you're looking at this, you're like, where do I start? You're going to start by converting your grams to moles. How do I know to do that? Well, I'm given by molar mass, right? So I'm going to immediately divide by the molar mass to figure out how many moles I have. And then I'm going to look back at what the problem is giving me. I have 32.9 kilojoules per mole. I'm trying to find the energy, which is probably measured in kilojoules, right? So if I set 32.9 kilojoules per mole, I multiply that by my moles. Moles will cancel out, leaving me with the energy. Don't be afraid to use the test to your advantage. All right? All right, it's almost 1 a.m. here, but we can do the hardest units, right? All right, unit 7, equilibrium. So what is equilibrium? I want to make sure you don't have a misconception about this. Equilibrium is not when we have equal amounts of anything. It's when the rates of the forward and reverse reactions are equal, and when the concentrations of the reactants and the products are constant. Could you have equal concentrations at equilibrium? Yes. K is equal to 1 when that happens. Is that normally the case? No. Equilibrium is when you get to this point where the concentrations are not changing. All right, we already talked about Q versus K. Q represents any point, the relationship between products and reactants at any point other than equilibrium. Know that the equilibrium constant and Q are going to be temperature dependent, so be careful with that. You don't have to have units with these, so that's one nice thing about these two annoying quantities. All right, so writing the equilibrium expression, you're going to not include any solids or liquids. So for example, this one would be concentration of H2 squared times the concentration of CO2 divided by the concentration of H2O squared. I know that I guess I put pressures in there instead. You can do pressures, you can do concentrations for equilibrium expressions. All right. So why does this matter? Why do we need to be able to do this? So if we are calculating K, so let's say I just put in all of those values, I have those concentrations, K is going to determine whether the forward is going to be favored or the reverse. So this is a small K value, so I would say that this is the formation of reactants would be favored in this case. So let's do a quick example. I like to use RICE where I'm writing the equation first and then filling in the rest of my table. So in this example, I'm given initial concentrations for each of my reactants. I'm going to assume then that I'm forming product since I don't have any product indicated yet. So when I start with my initial, I'm just going to start with those concentrations. I'm going to go ahead and put those in those rows. So now I have my initial concentrations in there. I'm assuming that I don't have anything originally for C, and I want to find the equilibrium concentrations. So I'm looking at my balanced equation. It is just a 1-to-1 ratio of those reactants, but I look at the product and I do have a coefficient of 2. So while I'm going to subtract X from each of my reactants, I'm going to add 2X to that product. Your change is going to reflect your stoichiometric coefficient, so the big numbers in your balanced equation. So I fill in the table, I have all of my values here, and I'm ready to find my equilibrium concentrations. So if I add up those two rows, right, I'd have 0.3 minus X for the concentration of A, same thing for B, and then 2X for C. But in AP Chemistry, you can always ignore X. So earlier in this, I said, assume the 5% rule always applies. You don't have to indicate it on your FRQ. You just assume it. You ignore X. So I'm going to actually write this as 0.3 is my equilibrium concentration for both A and B, and then I'm going to solve for 2X. So I am given my K value, and I know that that's going to be equal to the concentration of the products raised to the power of the coefficient, so it's C squared over the concentration of both my reactants. And this is because they are all, none of these are solids or liquids. So I'm just going to plug in those values, then I'm going to solve for X to find out my X value. And you're like, okay, great, we're all done, right? Be careful. We are asked to find the concentrations at equilibrium. The concentration of C is not X, it is 2X. So make sure to take that extra 30 seconds to find 2X. Another big idea from Unit 7 is going to be Le Chatelier's principle. And I'd argue that, predicting changes in concentration those are fairly easy, right? But it's pressure and temperature that can be a little bit more tricky. So if the pressure decreases, the reaction will shift to favor whichever side has more moles of gas. How do we know? You just look at the coefficients in the balanced equation. If we have equal moles, then a change in pressure won't impact the system at equilibrium at all. When it comes to temperature, you have to think about whether it's an exo or an endothermic reaction. Is heat released as a product or is it absorbed as a reactant? And that's really going to determine which side of the reaction is favored. If you are thinking about catalysts, catalysts do not impact equilibrium, but as we've talked about tonight, temperature absolutely affects K, or the equilibrium constant. And the last big topic from Unit 7 is going to be KSP. A little taste of what's to come in acid-base chemistry. So if we have 0.14 grams of nickel hydroxide dissolved per liter of water at 20 degrees Celsius, we want to calculate KSP. So first thing you want to do is write out the dissociation equation. So we have a solid precipitate just separating out into its ions. It's your net ionic equation, essentially, right, from earlier, making sure that you are including all of the charges and the states here. So then we want to determine KSP. So K, we already said, is the concentration of products over reactants. And I've had a lot of students ask me recently, wait, why is KSP only the concentration of products? Well, because products are the only ones that aren't solids. So in this type of situation, right, you have a solid precipitate as your reactant. That doesn't influence equilibrium. So therefore, KSP is going to look like it's only the concentration of the products, but technically it's still products over reactants. So let's run through just like doing the KSP ice table. So if we have this, again, the solid is not going to impact equilibrium. So we're starting out with no ions in solution. We're going to add S versus 2S for hydroxide, and then we're going to solve from there. So we know that KSP is going to be equal to the concentration of nickel times the concentration of hydroxide squared. So we're going to plug all of that in. It ends up being equal to 4S cubed. So now I can then solve. But wait, in case you wanted something else to memorize, KSP is a very valuable thing to have in the back of your head, so you don't have to run through the ice tables with this. If it is a 1-to-1 ratio, KSP is going to be equal to S squared. If it is a 1-to-2 ratio, like we just saw, it's going to be equal to 4S cubed, where S is referring to the molar solubility. It could be a 1-to-3 ratio. It's pretty rare, but that would be 27S to the fourth. Again, if you don't have these memorized, you can just write out the ice tables and figure it out, but I don't know. It's kind of easy just to remember this one. All right, back to the problem we are working on. So let's say we have this. We are given the KSP, and we want to solve for that S value, the molar solubility. So we were given initially, we had 0.14 grams dissolved per liter of solution. So if we then use our molar mass, we can figure out how many moles per liter. So now what we want to do is we want to take that one step further. So if we're looking at this reaction again, sorry, these animations are annoying. We want to solve for KSP. So we just plug S in times 4 cubed. So, sorry, we're going to plug S in. It's going to be cubed times 4. Don't mess up the algebra with this. You've put in so much work to do this. Just take your time with this and don't make a silly mistake. So this ends up being 1.4 times 10 to the negative 8th. Again, this is an equilibrium expression. We are not going to have units associated with this, but we can use K versus Q. Let's say we had a situation where we're looking at Q versus K. We can then use that to make a prediction about whether or not that precipitate is going to form. It's going to feel backwards because our solid precipitate is our reactant. But you can click on the laptop and watch a quick video going through that. All right, this is the big one, and this is probably the unit that you have probably, cried the most about. And you're not alone in that. It's okay. It's okay. I promise. Your teachers have cried about this unit too. When it comes to acid-base chemistry, though, remember that it is only worth 8 to 11% of the entire exam. And the questions that you see are not all going to be from those last couple objectives in this unit either. You are still going to see some of the basic questions. So make sure you're really comfortable with the basics. You know that an acid is a proton donor. A base is a proton acceptor. You're going to be looking for that moving H+ ion to try to figure out what's going on. You also want to be able to calculate the pH as the potential of hydrogen. It's just measuring that hydrogen ion concentration. It's a negative log of H+. These are the other equations that you need to be really comfortable with. The ones that I have on the right, the memorize these are just rearrangements of the pH equations, so you don't have to be messing around with logs on test day because time is money. All right, so H+ is going to be equal to 10 to the negative pH. OH- is the is equal to 10 to the minus POH. So whether you're looking at the H plus concentration or the hydroxide ion concentration, that's how we approach this. KW is also an important topic from Unit 8, just this idea that water can auto-ionize into H plus and OH minus. Why does that matter? You need to know that KW is equal to 1.0 times 10 to the negative 14th at 25 degrees Celsius. You don't have to memorize it, it's on your formula sheet, but you need to be able to then know if KW is equal to KA times KB, you can use KW to then solve for whichever you don't have, whether that's KA or KB. And that's really important with those weak acid or weak base strong acid titrations. All right, talking about strong acids, what makes an acid strong? Is it how low its pH is? Is it how dangerous it is? No, it's neither of those things. It's whether or not it dissociates in solution. So a strong acid or base is one that completely 100% ionizes in solution. I take hydrobromic acid, I add it to water, it's all going to separate out into H plus and Br minus ions. So also note that, of course, in chemistry, we have so many different ways to refer to everything. So dissociates is the same as ionizes or separates. So all of those ions just separate in solution. So how do I know the difference? You're going to memorize the 7 strong acids. So these are the 7 strong acids, pretty much the halogens minus hydrofluoric acid. Then we have nitric, sulfuric, chloric, and perchloric acid. Strong bases are a little bit easier to memorize because we're just looking at group 1 and group 2 hydroxides. So those are going to be our strong bases. So know the 7 strong acids so that when you look at a titration problem, you can immediately identify whether we're working with a strong acid, strong base, or weak acid, strong base, or weak base, strong acid titration. This is another simple concept from Unit 8. It's just being able to identify the acid, the base, and their conjugate pairs. So looking at this, we have a strong base plus a weak acid. The acid becomes a conjugate base after it loses that H plus ion. The base becomes a conjugate acid after it gains one. So again, you're following that moving proton, that H plus ion. And you also want to know that the weaker the acid, the stronger its conjugate base. The stronger the acid, the weaker its conjugate base. So those pairs are going to be oppositely related when it comes to the strength. All right, other things to know, pH and pOH of strong acids and bases. These are so easy to do because if I have a strong acid, when it completely dissociates in solution, guess what? The concentration of that strong acid is equal to the concentration of its H plus ions. So the pH is just going to be the negative log of whatever that initial concentration is. So in this case, this would have a pH of 4.82. All right, so just recognizing this is why you need to be able to identify whether something is strong or weak too. So this is a strong acid. I know it's going to completely dissociate. That means that the concentration of the acid is equal to the concentration of H plus ions. Same thing is going to be used for bases, except you're going to be using the pOH is equal to the negative log of that hydroxide ion concentration. The other equation you need to be really comfortable with is this idea that the pH plus the pOH is equal to 14. So we can easily find one or the other just by subtracting from 14. If you have a 1:2 ratio, it's like a little bit more complicated, but it's not that bad. So just be careful, especially when you're looking at titrations to make sure you're keeping an eye on those stoichiometric ratios and whatnot to make sure you don't forget to double that or divide it by 2. All right, so this is just examples of those. Weak acid base equilibria is where it gets a little bit more tricky. So acetic acid is a weak acid. So that means it's only going to partially separate in solution. So this is its dissociation equation. We have it separating into H plus ions and then its conjugate base. That's C2H3O2 minus. So what that means is in solution, the conjugate base is going to be in equilibrium with the weak acid. So we're going to want to find the Ka expression or the acid dissociation constant. So that's going to be equal to, guess what, concentration of products over the concentration of reactants, something you're pretty familiar with. Then we're going to set that equal to whatever value we're given. So if we're given a Ka value, we set that equal to Ka, and then H plus and C2H3O2 minus, because it's a 1-to-1 ratio, those are going to be equal. So Ka is going to be equal to x squared over that initial concentration of the acid. Solve for x. Once you have x, you have your H plus concentration, and you just plug it right in. How does that differ for bases? So bases will be using Kb, which is the base dissociation constant. So that's equal to the hydroxide concentration times the conjugate acid concentration divided by that initial weak base concentration. If you end up solving for the pOH, again, just subtract from 14 and you'll have your pH. So here are just some of those associated equations. Again, pKw or Kw is really important to remember. Kw is equal to Ka times Kb. Again, that's what you need for weak acid, strong base titrations when you're trying to find the pH at the equivalence point. So let's say I wanted to find the pH of a 1.2 times 10 to the negative third molar solution of acetic acid if the Ka is equal to 1.8 times 10 to the negative fifth. So we're going to then remember the acid dissociation constant is equal to the concentration of H plus times the conjugate base. That's going to be equal to x squared over the initial concentration. Solve for x. X is going to be equal to H plus. So then pH is the negative log of H plus. The pH is going to be 3.83. All right, pH and pOH equations. So these ones are pretty straightforward. You also want to remember this. So the concentrations that H plus concentration is going to be equal to 10 raised to the power of the negative pH. This is not on your formula sheet, but again, I don't really want to be rearranging the log on the day of the test. I don't think you do either, so just memorize those. Which brings us to titrations. Dun, dun, dun. Yeah, you'll be fine, I promise. All right, so titration tricks. When it comes to strong acid, strong base equations, you're not going to have an equivalence point. Why? Sorry, you're not going to have a half equivalence point. You are absolutely going to have an equivalence point. It's going to happen at a pH of 7. With any strong acid, strong base, the equivalence point happens at a pH of 7. You do not have a half equivalence point because you don't have a buffer system at any point. So you have no buffer region, just the pH of 7 at the equivalence point where you have moles of acid equal to moles of base. It gets a little bit more interesting with the weak acid, strong base, or weak base, strong acid titrations. With these, you will have what we call the buffer region leading up to that equivalence point, where you have the weak acid plus its conjugate base in solution, leading to a slow increase in the pH before we hit that equivalence point. So the cool thing about these types of titrations is that half of the volume to the equivalence point, the pH is equal to the pKa, or the pOH is equal to the pKb. Why is this the case? If we think about the Henderson-Hasselbalch equation, at the half equivalence point, half of our moles of weak acid have been changed into the conjugate base. So the moles of the moles of weak acid and conjugate base are equal. So therefore, that cancels out. And then we just have the pH is equal to the pKa. And here are some other acid-base chem hacks. So when it comes to Ka and pKa versus the strength of the acid, the higher the Ka value or the lower the pKa, the stronger the acid. If you're choosing a buffer, we haven't really talked about buffers much yet, but you're going to look for the conjugate acid-base pair, which never includes a strong acid or a strong base. If you're looking for an indicator for a titration, you're going to look for the one that has a pKa that is closest to the pH at the equivalence point. And we didn't talk about the distinction between equivalence and endpoint. Equivalence point is the point at which the moles of acid and moles of base are equal. The endpoint is the point at which you stop the titration. So ideally, they are very close to each other, but that's not always the case. All right, if we were looking at this multiple choice question, this is actually a super, super easy question because you're going to look at it, you're going to say hydrofluoric acid is a weak acid versus sodium hydroxide is a strong base. Weak acid, strong base titration. At the equivalence point, I'd expect the equivalence point to trend towards basic, so it's going to have a pH of greater than 7. Got to memorize those 7 strong acids. This is another example of an FRQ. Titrations tend to show up on the FRQs. This one was just a simple volume reading. This is an example of the 1 sig fig style question too. So with this one, you want to make sure you're estimating 1 digit past the smallest marking. That's always true, whether you're looking at a burette, graduated cylinder, always estimate 1 smaller than the smallest you can see. Obviously, there's going to be some room here. We're all going to see differently and estimate differently, but as long as you have those 2 decimal places, right, you're showing that you're estimating into the 10th place, you will be good. Not all titration calculations are tricky. So this is an example of just a straightforward one. This is just where we have the concentration of potassium permanganate, and we want to find the moles that reacted. So we just need to focus on the fact that the endpoint has been reached. We know molarity times our volume is going to give us our moles. We're just multiplying that out, and we have our answer. So It's not always as tricky as with weak acid, strong base titrations. So don't get intimidated by these questions. You can still get easy acid base points. All right, but moving on to the harder side of things in Unit 8, the Henderson-Hasselbalch equation. So this is just that the pH is equal to the pKa plus the log of the conjugate base over the weak acid. That can either be moles of each, or it can be the concentration. If we are looking at the same solution, right, if we have moles of conjugate base over moles of weak acid, technically they're going to be in the same volume, so there's no reason to actually change that into concentration. We can also use this POH is equal to the pKb plus the log of the conjugate acid over the concentration of the weak base. So know that it can be used interchangeably. When it comes to buffers, so buffers are going to be systems which resist changes to pH, and they're always going to be a mixture of they're always going to be a mixture of a weak acid plus its conjugate base, or weak base plus its conjugate acid. Key focus here is that it is never a strong acid or a strong base. If you want to learn more about how buffers work or how to do those those calculations, go ahead and click those links. And the buffer capacity, which is the amount that the buffer is able to withstand before we start seeing those spikes in pH changes, are going to be dependent on the concentrations and the ratio between those two systems. So the higher the concentration, the better the buffer is, the longer it can withstand changes to its pH. And by withstanding changes, I mean you can dump some strong acid or strong base in there and it's going to seem like the pH does not change. All right, but when it comes to pH calculations, this is the hardest thing. I think this is the hardest topic covered in AP Chem, but I promise with practice, you can figure this out too. So when it comes to these types of titrations, you want to identify whether you are working with a weak acid, strong base, strong acid, identify the strengths of your analyte and your titrant. Start there. Then figure out where on this curve you are at the point where you're asked to find the pH. If you need to, you might need to find the volume needed to reach the equivalence point. You're going to just find the moles of whatever you're given, use stoichiometry to find the moles of what you're looking for, and then work backwards to find the volume. If you know your equivalence point occurs at a volume of 20, but you're asked to figure out the pH at only 10 mils, you're going to be like, oh wait, this is super easy. At the half equivalence point, the pH is equal to the pKa. I'm going to take the Ka value that's given, I'm going to plug that into the negative log. I'm going to take the negative log of that, and I will have my pH. All right. And it's now 1:20 a.m. and my kids are going to be up in like 5 hours. So I got to wrap this up. But let's look at Unit 9. If you are looking for a full Unit 9 video, know that I have a 25-minute long video where I go through every aspect of Unit 9 that you need to know. Big ideas are going to be electrochemistry, that's new, calculating the cell potential, understanding electrolysis and Faraday's law, and understanding how to make predictions at nonstandard conditions. So using the Nernst equation to figure out how a change in, let's say, concentration is going to impact the cell potential. And I know electrochem is very new to you and you may not have even covered it in class. But here are just the basics, just really quickly. So we have two types of electrochemical cells. We have the galvanic or voltaic. Those are thermodynamically favored processes. And you'll see a salt bridge in these cells like you see in this image. We also have electrolytic cells. These are going to be non-spontaneous cells, which are forced to run with the addition of a battery or some kind of electrical power source. When we look at our electrochemical cells, we always have an anode and a cathode. Oxidation is going to happen at the anode, so the loss of electrons happens at the anode. The cathode is where reduction happens, where we are gaining those electrons. So we have this exchange of electrons, a transfer of them. They're always going to move away from the anode and come to the cathode. And as the cell operates, the mass, if it is not an inert or non-reactive electrode, then you're going to accumulate mass on that anode. So you can remember the cat gets fat. So we don't want to reach equilibrium with these electrochemical cells because as soon as we reach equilibrium, our cell is no longer operating. We have a dead battery. So this is the one time where we're not talking about equilibrium with electrochemical cells because if we reach equilibrium, again, what's the point? We don't have an electrochemical cell any longer. And the whole goal with this is to transfer energy. So whether we're looking at this voltaic cell where we are transferring chemical energy and changing that into electrical energy, or doing the opposite with an electrolytic cell. And you may have heard me say the cat gets fat. Electrochem is so counterintuitive. So these are some mnemonic devices just to help you with the little nuances of electrochem. So oil rig is something you probably learned with redox. Oxidation is loss, reduction is gain, just talking about how those electrons are transferring. An ox and a red cat will help you remember where each of these processes happens. Oxidation happens at the anode, NOx, and reduction happens at the cathode, the red cat. We can remember the electrons come to the cathode. You might have to just draw in the direction of the electrons, the flow. You have to identify where oxidation is happening. That's going to be your anode. They're going to move away from that. They're going to move over to the cathode. And then again, as the cell operates, the cat gets fat. So the mass can accumulate on the cathode. Here's just the comparison of the two cell types. Again, we have voltaic or galvanic on the left and electrolytic on the right. Difference is whether or not they are favored processes. So we have a positive cell potential with voltaic and a negative cell potential indicating an unfavorable reaction that we have to force to occur with the addition of an external power source. So those are the differences between those. Remember that with the voltaic cell, you have to have a salt bridge, which is essentially just going to balance the charge. So it's going to be some kind of liquid in there, typically potassium nitrate, something like that. And then if we look, what's going to happen is all of the cations are going to go to the cathode and the anions are going to move to the anode. Kind of nice that those match up. And then this is a calculation we see just about every year, and unfortunately it's not on the equation sheet. So if you were asked to find the cell potential, the E dot cell, that's going to be equal to the cell potential at the cathode minus the cell potential at the anode. So let's say you're given a table of reduction values. You are literally going to identify which one is the reduction. That's the cathode. We're going to start with that, and then we're going to subtract the value at the anode. It's possible your teacher has taught you to reverse the sign of the oxidation reaction at the anode, in which case you just be adding these two values together. I think it's easier just to do cathode minus anode, so you don't have to worry about that at all. All right, another big equation from Unit 9 is going to be the free energy equation. So delta G is equal to negative NFE. Faraday's constant is something you will use in a lot of different ways. Pay attention to those units. So Faraday's constant is 96,485 coulombs per mole of electron. When you are doing Faraday's laws, you're doing those conversions, so you want to see the mass plated at one of those electrodes. Got to keep in mind that this constant can be used to make conversions between moles of electrons to whatever you're looking for. And then when it comes to non-standard conditions, you gotta know what is a standard condition first, right? So in an electrochemical cell, we're looking at concentrations of 1 molar or 1 atmosphere of pressure for gases and a temperature of 298 Kelvin. So at this instant, right, Q is equal to the concentration of products over reactants, so Q equals 1, and the cell potential is dependent on the concentrations of those substances. So if we're at non-standard conditions, any concentration other than that or any temperature other than that, we have to figure out how we're going to make predictions about that cell potential, because in electrochemical cells, we cannot use Le Chatelier's principle. Why? Because we are not at equilibrium, right? The system is not at equilibrium, because if it's at equilibrium, the electrochemical cell is not working. All right, so how are we going to figure this out? So what you're going to do is you're going to look at your concentration in relation to Q, and you're going to use the Nernst equation. Thankfully, this is on the formula sheet. You will never have to pull out a quantitative value for that cell potential, but you will have to predict how this might shift. So you're going to think about Q. So if the concentration of your products, for example, increase, Q is going to increase because Q is equal to the concentration of products over reactants. When Q increases, and we're subtracting that from the initial cell potential, our new cell potential is also going to increase. So be able to make accurate predictions looking at those changes to figure out how that's going to impact the cell potential. And in case you'd rather just memorize it at this point, here's what to expect with those changes at non-standard conditions. All right, you made it. So at this point, sleep is more important than cramming until 4 a.m. when you have an 8 o'clock a.m. exam. So if you are watching this at 1 a.m. right now, I want you to close that laptop and go get some sleep. You also want to pack your bag Monday night, have it all ready. Again, 8 o'clock is an early exam if you're on the East Coast. Have everything you need. Put your calculator in there, your pencils, whatever you need for test day. Get it ready so you're not running around that morning. Don't forget to eat. Get to your test site early. Laugh, cry, get ready together with your fellow test takers who have all suffered through AP Chem. And mention Coulombic attraction as often as possible. That's a joke, but it is useful. I also just want to remind you that a score does not define you or your experiences in AP Chem. You have learned so much through the struggle that is AP Chem, and you're going to walk out of this test and out of this class a stronger student. I will tell you, while I was at UVA, I was teaching a Gen Chem lab for pre-med majors. And what was the class that was forcing all of them to reconsider all of their career choices and switch out of the major? It was Gen Chem. So know that whether you are planning on taking Gen Chem next year or going into STEM or just, going to college next year, you are going to be ready after suffering through this class. So I am so proud of you, and have fun. Show them what you got.